Hi and welcome to the 6th year higher level maths video where we are working with the revision worksheet 7, which is a section B calculus question. So the question is, in a 100-meter race, sprinters typically reach their top speeds about halfway through the race and try to maintain that speed for as long as possible. A student analysed the sprinter's performance over the course of a particular race and determined that the speed of the sprinter can be approximated by the following model. So V of t, V standing for velocity, which is another word for speed, we have three different sections. So when time is between 0 and 0.15 seconds, they tell us underneath that V is in meters, t is time in seconds. So between 0 and 0.15 seconds, the sprinter doesn't move. So that's like a reaction time. So, you know, when the starter gun goes or when a whistle is blown, whatever starts it, they take just a very split second before they start moving. The second part of that function is a negative quadratic. So if you can imagine, this is what's happening. So we have a very slight delay to start. And then we have a negative quadratic like this until it hits its max speed. And that's the third section, which ends up straightening out like this and going for as long as they can. Now this is a continuous graph because you can't randomly jump from one speed to another. You have to go through all the speeds. Speeds are continuous, or speed is continuous. So we're going to use that fact to answer the first part, which is find the value for k. So there's two different things we know with the function that has k. So let's just take the function v of t, and I'm literally just taking the middle bit because that's the bit that has the k. And there's two different ways to work this. So the first way is v of 0.15. So when you sub in time is equal to 0.15, so the very start of that, then that should be equal to 0. The second section, or the second way you could do this, is when you sub in time as 4.5, it should equal the speed of the third section, which is 11.3535. So it's completely up to you which way you want to work. It doesn't really matter. Both should give us the same answer. Let's go for 0.15. So 0.15 means I'm going to sub in minus 0. Watch that minus when the negative is in the front. It's so easy to lose it. So minus 0.6 times 0.15 squared plus 5.4 times 0.15 minus your k equals 0. So let's put these two straight into the calculator, these two terms. So we get 0.7965 minus k equals 0. So k equals 0.7965. It didn't tell us to round. That's all the digits that we have. Like I said, if you want to go and try it with the 11.3535, you should get exactly the same answer. So part 2 asks us to sketch the graph of v as a function of t for the first 7 seconds of the race. So the first section is really easy. So 0.15. So 0.15, if you want to think about that in terms of where we're going on the graph. So it's a little bit less than a quarter. So we're kind of just going to about there. And then we're going to start into our negative quadratic curve. The second piece that I usually do is not the second quadratic piece, but actually the last piece because it's easier to see. So 4.5. So I'm talking about here. And I'm going up to about 11. Now it's saying sketch because how accurate can we really be? So there's 4.5 and 11. And we want about 11.353. So it's about here. And you're drawing a straight line across. Straight, I haven't got my ruler on this, so you need a nice straight line there. And then you're going to work with the middle function and work with all the numbers in between. So we'll do v1. So that'll be minus 0.6, 1 squared plus 5.4 times 1 minus, our k is minus 0.7965. So the k was positive, but there's still a minus in here. And you work that out. and you get 4.0035. So the point that you're plotting is 1 and then just above 4, so right there. And then you do the same for V2, V3, V4. You don't have to go past that because 4.5 we've already put in. So you can do this out the long way if you want to use the function function on your calculator. That's absolutely fine. And we get 7.6035, 10.003, and 11.203. When you graph it, it should look something like this. Now, it's not perfect, but you can see the 3 distinct sections. We have that lovely straight line to start, although it's very small. We have that curve of the negative quadratic, and then we have the lovely straight line drawn with the ruler then at the end. So part 3 then says, find the distance traveled by the sprinter in the first 4.5 seconds of the race. Now, this is interesting because we're not going to be able to use distance, speed, and time because the velocity was changing, and it was changing in a way that graphed a quadratic, which means the acceleration was in there and there was something happening more complex than distance, speed, and time allows. So we're working here with integration. So our integration is distance or displacement s. When we differentiate it, gives us velocity, which when we differentiate gives us acceleration. And then if we want to go backwards, acceleration we integrate to get velocity. When we have velocity we integrate to get s, stands for distance in this case. Now, the first 4.5 seconds, now I'm not going to bother with the first part of that function because 0 is just 0. So all I'm going to do is I'm going to integrate. Now, I'm going to use my limits of integration. I'm going to integrate between 0.15 and 4.5 to get the distance between the time is 0.15 and the time is 4.5. So I have that minus 0.6 t squared plus 5.4 t minus 0.7965, and that's with respect to t, so dt. So our rules of integration, because we're working with simply what we would usually have an x to a power, it's t to a power. We're going to add 1 to the power, take 1 away from the power. So this becomes minus 0.6 t cubed divided by 3 plus 5.4 t squared divided by 2 minus 0.7965 t. It's divided by 1, but you don't need to put that in. We don't need to add the c because we're using our limits of integration to evaluate this. If you want to simplify it a little bit easier to make, if you want to simplify it a bit to make it a bit easier to put in your calculator, that's fine. So this is 0.2 t cubed plus 2.7 t squared minus 0.7965 t, and we're still evaluating that between 0.15 and 4.5. So that is going to be minus 0.2 times 4.5 cubed plus 2.7 times 4.5 squared minus 0.7965 times 4.5. Take away, it's a bit smaller, so a bit of room to work, minus 0.2, 0.15 cubed plus 2.7, 0.15 squared minus 0.7965, 0.15. So what we're going to do is we're going to evaluate each square bracket and then do the subtraction. So that first square bracket gives us 32.86575. Take away that second bracket, it's actually a negative, minus 0.0594. And when we get that, and well, effectively it's an adding rather than a subtraction, we get 32.92515 meters. Now they didn't tell us to round that, so I'm going to leave that as is as we move into the next part. So it says, hence find the sprinter's finishing time for the race. Give your answer correct to 3 decimal places. So what's really important at the very start of this question is they told us that the whole thing was 100 meters. It was a 100 meters race. So we know that they've actually already run 32.92515. So what is left to run? We're going to take these two numbers away. So we have our 100 take away 32.92515. And we end up with 67.07485 meters left to run. This is where the sprinter, according to the model, was running at a constant speed. So that constant speed means we can go back to using distance, speed, and time, because constant speed means there is no acceleration. So all we care about is that last speed. So our sprint really is divided into 2 pieces. So the first piece was up to 4.5 seconds. So the time for the first section is 4.5 seconds. That came from the graph. And in that, we know that they ran 32.92515 meters. In the second section, we don't know the time yet, but we do know, I short really this S equals, we do know that the S is equal to 67.07485. So because we also know the speed for this section, what we're going to do is go back to this distance, speed, time. Now that S is a capital S, which means it stands for speed. But what we're going to use is time is equal to the distance divided by speed. And we, again, are allowed to use this because we know that there is no acceleration here. So we have 11.3535 meters per second here. Meters per second there. So let's work out our time. So our time is equal to the distance, which is 67.07485 divided by that speed, which is 11.3535. And when we put that into the calculator, bearing in mind that we want to keep this to 3 decimal places, I get 5.90. It's 7.8, but I'm going to put it to 8 seconds. Now, that's not my final answer because remember, this is only the second section. So I have to add 4 to this because that first piece where he was accelerating, that went on, so 4.5. So we have 4.5. So that gives us plus 4.5. And we get 10.408 seconds to run the total race. So it would be very easy to forget to go back and do that 4.5, or it would be very easy to not have noticed that 100 meter at the start. So just be careful. So part B of this question, a model for an Olympic standard 100-meter sprinter was developed by mathematicians. The speed of the sprinter may be calculated using the following formula. So here we have an exponential function, W of t, and it says where t is time in seconds from the starting signal. So find the maximum speed of the sprinter correct to decimal places. So we want to find the maximum of the function, so we're going to use differentiation here. So I'm going to find W of t. But before I do that, what I want to do is simplify the W of t function itself. As is, it looks a bit complicated. It's not, but it just may be easier to differentiate if we multiply in that coefficient. So we'll end up with something like this, e to the power of minus 0.8t plus 0.03 minus 0.03 e to the power of 0.3t. Now, it's not that complicated to work it in its original form. It's not the product rule because officially the 11.7 and the 0.03, there are coefficients there. They're not in terms of t, so you don't need the product rule. You could use the product rule, it's just going to be much longer. I do think the most straightforward way to work this is just by multiplying in those two coefficients and then working with our derivative, which is w dash t. So any constants are going to disappear. So the 11.7 and 0.03, when we differentiate a number on its own, it goes to 0. Anytime we differentiate e, so you can go to your log tables and look up the rules of differentiation. This is ax, so e to the power of ax. So there's something in front of the x, or in this case the t. So how this actually works is the minus 11.7 just kind of sits there, and then we bring down, it looks like in the formula it's the coefficient, it's actually the derivative of the power. Now if the power has just a t or just an x, then yeah, the derivative and the coefficient are the same thing, but you'd have to be careful in case that was a t squared. So that's what it looks like, and then the same thing happens over here, and we bring down the power 0.3 e to the power of 0.3 t. The e to the power never changes, and it's really important that you have your rules of differentiation open in front of you whenever you're doing a differentiation question. It's very easy to get confused and to apply the wrong rule. So I'm going to tidy this up. So I'm still on the first derivative, and this works out as minus by minus is plus 9.36 e to the power of minus 0.8 t, and then we end up here with a minus 0.009. When you put that into the calculator, it will actually give that to you in scientific notation. So it's really important that you're able to work with scientific notation. You're able to convert it into a decimal by moving the decimal place, or leave it in fractional form if you're not comfortable working with scientific notation. So in order to get the maximum, we let the derivative equal to 0. So we have 9.36 e to the power of minus 0.8 t minus 0.009 e to the power of 0.3 t equals 0. I'm going to bring, you can do it multiple ways. I'm going to bring one to each side. So I'm going to leave the 9.36 e to the power of minus 0.8 t here, and I'm going to bring over the 0.009 e to the power of 0.3 t. What we want to do, and this boils down to the most simple linear equations we're ever going to solve, we want to get letters on one side and numbers on the other. Usually adding and subtracting does this, but actually in this case, adding and subtracting is not enough. We're going to actually have to use division. So what I'm going to do is I'm going to divide this side by minus e. So I'm going to get rid of it on that side, but I also then need to do it over here. And then I'm going to get rid of the number from this side. So I'm going to also divide by that. And I'm going to balance that out by putting it there. So the number pieces or the coefficients will cancel here. The e's to the power cancel on that side. And we end up with 9.36 divided by 0.009 is equal to e to the power of 0.3 t divided by e to the power of minus 0.8 t. Now this is much easier to work with because I can simplify this, which is 1040, and then with the e's, because I have a base to a power divided by the same base to a power, we can take away the powers. But when we take away a negative, just be careful with your signs here. We have a minus 0.8 t, which will simplify down into 1.1 t because we'll end up adding the 0.8 t. So this is the equation I'm working with. E to the power of 1.1 t is equal to 1040. So we need to work with logs to get rid of that e. I'm going to take the natural log of both sides, which gives me 1.1 t is equal to the natural log of 1040. You have a conversion formula in your log tables. It's on your rules of indices page, or you can use the circle method here. You can put the natural log of 1040 into your calculator, but it's going to be a decimal. I'm not a huge fan. So what I'm going to do is simply divide this by 1.1. It can be easier to put the division into your calculator as a division sign. And we want this correct to 2 decimal places. So when I do that, I get 6.32 seconds. Now, it's really important in these section B function questions to really focus on what you were asked and what you've got. So they asked us for the maximum speed. So we followed what we would always do to get the maximum of a function, and we differentiated and let it equal 0. But what we got was time as our answer. Now, because we're working with this formula here, what they've actually given us is the time when the maximum speed happens. So we now have to go and sub back into my formula at 6.32 seconds. So when I do that, I get 11.71 minus e to the power of 0 minus 0.8, 6.32. Plus 0.03, 1 minus e 0.3 by 6.32. That can go all into your calculator, and I want 2 decimal places, and we get 11.46 meters per second. So in terms of basic functions, when we get the first derivative and let it equal to 0, we're usually finding a value for x. So we find the x value where the function is the biggest or the smallest depending on the function. We then sub it back in to find the value of y, which will actually give us the height of the function. That is the actual maximum of the function. So remember, function f of x is another way to say y. In this case, the y is w of t. So we want the w, which represents that speed. So part 2 of this says find an expression for the distance traveled by the sprinter after time t. So this, if we remind ourselves, is the formula for speed, and I want to find a formula for distance. So how I get from distance to speed, I'm going to do it over on the right hand side here. We start with s, which actually stands for displacement. When I differentiate this distance or displacement, I get velocity or speed, and when I differentiate that again, I get acceleration. So I'm currently here and I want to get back there. So in order to go back, I'm going to need to differentiate. So I'm going to write this as s of t. You can write it as simply s, that's fine. And I'm going to integrate this as 11.7, I'm going to use square brackets, I'm going to multiply this in as well, just like we did with the differentiation, because that will help with our integration as well. 0.8t, and then a plus 0.03 minus 0.03 e to the power of 0.3 t, and that's all with respect to t, so dt. That is what I'm differentiating. I do not have limits of, that's what I'm integrating. So I don't have limits of integration, which means when I do this, I'm going to have a plus c, that constant of integration, and I'm going to need to figure out the c. So in your log tables, go to your page where it gives us the rules of differentiation. And what we're going to get is this becomes 11.7 t. Now, e, be careful again not to just add a 1 to your power and divide by your power, because that is when we have t to a power. Here we've e to the power of t. So what I'm going to have is 11.7 e minus 0.8 t, nothing changes, but I divide by the derivative of the power, or it kind of again looks like the coefficient of t. I get 0.03t. I am dividing by the power here because it's power 1, nothing is happening. So I'm minus 0.03e, 0.3t, and again I'm dividing by 0.3. This is in our log tables as e to the power of ax, and then I have a plus c. So you can tidy this up if you want. I'm going to do that before I actually do any substitution. Get 11.7. This becomes 14.625 e to the power of minus 0.8t plus 0.03t. And then here I get minus 0.1 e to the power of 0.3t plus my c. I want to get rid of my c, but they didn't give me anything to use. But if we think about what this model is actually showing, it shows the speed given the time. So what we would know is you will always start a race from rest. So when speed is 0. So when t is 0, we know that the speed will be 0. But we also know that how far have you traveled at the start, and the answer will be, well, nothing. So if I sub in 0, my distance or displacement should also be 0. So when I do that, I dropped my t here. So when I do that, I'm going to get s of 0, which gives me 11.7 times 0 plus 14.625 e to the power of minus 0.8 times 0 plus 0.03 times 0 minus 0.1 e to the power of 0.3 times 0 plus c, and that should all equal 0. Now this goes to 0, that goes to 0 as well. When we have a number multiplied by 0, it goes to 0, but then I'll have e to the power of 0, which will actually be 1. So what we end up with is 14.625 minus 0.1 plus c equals 0. And I end up then with c is equal to minus 14.525. Now I can write my final expression for the distance. So my final expression for distance is s of t. Now you could just call that s if you wanted, but s is our symbol for distance, really for displacement. But our s of t is equal to 11.7t plus 14.625 e to the power of minus 0.8t plus 0.03t minus 0.1 e to the power of 0.3t minus what we just worked out as that coefficient, that's c, the coefficient of integration, 14.525. So the final part of this question says, hence, show that the sprinter completes the race in less than 10 seconds. So maybe an obvious goal for this is say, well, I know that the distance of the race is 100 meters. Let this equal to 100 and see if we can solve. But it's quite a complicated piece to solve. And most students wouldn't be able to at this point with what we know. So what I would suggest is to think about this in a different way. So maybe it's not the obvious way to approach it. But if we want to show that he finishes the race in less than 10 seconds, let's actually plug 10 seconds into this formula and see what happens. Because this is a formula for distance. So if we find out how far he runs in 10 seconds, if that's bigger than the 100 meters, then of course he would finish the race in less than 10 seconds. And it's a much more straightforward method. It's much nicer maths to do. So I'm going to sub in 10 everywhere we have a t, so 625 e to the power minus 0.8 times 10 plus 0.03 by 10 minus 0.1 e to the power 0.3 by 10 minus 14.525, and I figure out the distance that a sprinter runs according to that formula in 10 seconds is 100.77 meters, which is greater than the 100 meters of the race. So therefore, the sprinter would have to finish the race in less than 10 seconds. So the sprinter completes the race in less than 10 seconds. So if you're looking at that going, I never would have thought of that. This is why practice is so important, because you're going to expose yourself to all these different types of questions and all these different ways of thinking in maybe not the most straightforward way, but actually this little bit of a tweak of thinking made the sum so easy to do. So looking for a different way. So don't just power into solving equations, especially if they're very, very complicated. Think, is there a better way to do this? So if they had asked us to find t, of course, there's nothing we can do. But the fact that they said less than 10 seconds, and I suppose, you might go, oh, well, if I show it's 9, does he finish the race? But be careful, because time is continuous. So it doesn't mean he finished it in 9 seconds. It might be 9 point something. So I would say just subbing in 10, proving it's a longer distance than the race is the best way to approach this part of the question.